Section 4.4, the mean value theorem. So I want to begin this section by saying that a lot of things in this section are going to be proven. Okay, I'm going to go about some methods of proof. Now, I do not expect that you will be able to regurgitate. Okay, that wouldn't be very good critical thinking anyways. I don't expect you'll be able to regurgitate these things, but I do expect that if you continue on in mathematics, that seeing the proofs of these things, or having at least been exposed to them, is a worthy thing. So we will use each of these theorems that we prove, but I am going to embark on making sure that they are true. So the first is Rolle's theorem. So for Rolle's theorem, we need to have a continuous function over a closed interval a to b. It also needs to be differentiable. So let's take note of these hypotheses. Continuous function, continuous, over the closed interval a to b, and differentiable over the open interval ab. We also need to have that f of a equals f of b. Then we're guaranteed there exists one point, at least one point, in that interval such that f prime of c equals 0. So there are three examples here. If the endpoints are equal, that's one of the hypotheses. It's continuous and differentiable. But if the endpoints are equal in any of these cases, there has to be at least one point where we have a tangent line. Now, the degenerate case is you could have a function that looks like this. Now, every point in that interval has a derivative of 0. The idea, though, is we're saying there can be at least one. There has to be at least one if it is continuous over a closed interval, differentiable in there, and the endpoints are equal. So let's apply this to example 1. For each of the following functions, verify that the function satisfies the criteria stated in Rolle's theorem, and find the values of c where f prime of c equals 0. So we're going to apply the method that we used in the last section for this. So first, let's just go ahead and say, does it verify all those conditions? So is it continuous on -2 to 0? Yes, it is. Okay, it is a quadratic, so it is continuous on that interval. We also know it is differentiable. It's differentiable everywhere, but it is specifically differentiable on that interval. And f of -2 is that the same as f of 0? It is, because those are both zeros of this. Okay, so both of those values are 0. So now we will take f prime of c equals 0. We are going to find the value of c. Taking the derivative and evaluating at c, we get 2c plus 2 equals 0, which tells us the value of c we are seeking is -1. There we have found all the values of c that are guaranteed in that interval. All right, part B. First, is this function continuous on the interval -2 to 2? Yes, again, because it is a cubic. It's a polynomial. It is also differentiable on -2 to 2 specifically, but it's differentiable everywhere. All right. Last is f of -2 equal to f of 2. Well, if we evaluate that, that would be -8 plus 8, that's 0. Evaluating 2, that's 8 minus 8, that is also 0. So yes, those two endpoints are equal. All right. So then we will take f prime of c, set it equal to 0, and find the values of c. All right, so that would be 3c squared minus 4 equals 0. Adding 4 to both sides, dividing by 3, and then taking the square root, we get c equals plus or minus 2 over the square root of 3. The square root of 4 is 2. The square root of 3 is square root of 3. So those are our values of c that we're guaranteed by Rolle's theorem. All right, part C. Is it continuous? And it's understood on that interval 1 to 3. Yes, it's a polynomial. Is it differentiable? Yes. And is f of 1 equal to f of 3? The two endpoints, are they equal? Valuing at 1, that is 2 minus 8, negative 6, so that is 0. Evaluating at 3, 18 minus 24 plus 6, yep, that's 0 as well. All right, so those two are, in fact, equal. So we'll take f prime of c equals 0, and then solve for values of c. The derivative of that function is 4x, so that'll be 4c minus 8 equals 0, and that shows that c is equal to 2. So that is our value of c guaranteed by Rolle's theorem. Now, this diagram here is meant to tie into the next theorem, the mean value theorem, but I want to make a little bit of sense of the mean value theorem first. So, let f be a continuous over the closed interval a to b and differentiable over the open interval a to b. We have parentheses there. Then there exists at least one point c in that interval such that f prime of c equals f of b minus f of a over b minus a. All right. This is actually the slanted version of Rolle's theorem. So whereas Rolle's theorem had the two endpoints are equal, what if the two endpoints are not equal? All right, well, first we have this. The f of b minus f of a over b minus a. F of b minus f of a over b minus a. There we go. All right, so that would be this line right here. That is the average rate of change on a, b, that interval. That's the average rate of change. All right, now, for each of these two places right here, this is f prime of c. This is the instantaneous. Try that again. Instantaneous rate of change at C2, because that's the point that it's at. And then similarly, this down here is the instantaneous rate of change at C1. So this says there is one point, at least one point in the interval, such that the instantaneous rate of change, okay, that is the instantaneous rate of change, equals the average rate of change. Okay, so let's begin the proof. Actually, think about driving from here to the nearest big city. Okay, now you might say I went, 3 hours at, 70 miles an hour. You can think about your average rate of change, the time and the distance. But if you think at every instant that of your driving, if you looked at your speed at every given moment on the speedometer, there's some point where you were going the average rate of change. You might not have always been going your average of 75 miles an hour, or more likely 55 miles an hour, hopefully. But there's some point where you are going, your instantaneous rate of change is the same as your average. Okay. All right, so let's go ahead and begin this proof then. Consider the line connecting a f of a and b f of b. They have to be points on this continuous function. So the slope of that would be f of b minus f of a over b minus a. That will be the slope of the line connecting those 2 points. So the equation of that line would be y equals, I'm going to go ahead and get y alone. So the slope is f of b minus f of a over b minus a times x minus a plus f of a. Okay, so that is the line that goes to the 2 points. That is, looking at our graph, looking at that picture, that is this. That is the equation of that line right there. So that's the equation of that line. Okay. Now we're going to introduce a new function called, and we're just going to call it g of x, which is f of x minus that line. Make that a good fraction there. B minus f of a, b minus a, x minus a, plus f of a. Now, let's consider the 2 points. Now, because f of x is a continuous differentiable function on that interval, we can actually apply Rolle's theorem eventually. But let's consider the endpoints. G of a. G of a would be f of a minus f of b minus f of a over b minus a of a minus a plus f of a. Hopefully you notice this is going to be 0, and then f of a minus f of a is also 0. So g of a equals 0. Now g of b. Plugging in g of b, that will be f of b minus f of b minus f of a over b minus a times b minus a plus f of a. These two terms cancel, which then allows for these two terms to cancel, which allows for the entire thing to be 0. Alright, so because our endpoints are the same and this function is continuous, differentiable, the endpoints equal, then there exists some point c such that g prime of c, which is f prime of c minus f of b minus f of a over b minus a equals 0, which then implies that f prime of c for that point we have just found that we've guaranteed by Rolle's theorem equals f of b minus f of a over b minus a. Okay. Which is what we were trying to prove. All right, that is the proof of the mean value theorem. Now, let's apply that. Apply that to this next example. For f of x equals the square root of x over the interval 0 to 9, show that f satisfies the hypotheses of the mean value theorem, and therefore there exists at least one value c in 0 to 9, such that f prime of c is equal to the slope of the line connecting those 2 points, 0 f of 0 and 9 f of 9. Find these values c guaranteed by the mean value theorem. Okay, well, I can certainly say it is continuous from our previous, actually our first section finding derivatives by limits. Okay, I remember we used the square root of x. It is continuous at 0 in particular, and so it's continuous overall. And that function is differentiable, so we always want to write those down. So let's go ahead and say that is continuous. It's differentiable. So therefore, there exists one value of c. One value c at least in 0 to 9, such that f prime of c is equal to the slope connecting those two. So therefore, there exists a c in 0 to 9 such that f prime of c equals f of 9, because our endpoint there is b is 9 minus f of 0 over 9 minus 0. Now, this implies, since the derivative of that function, x to the 1/2, is 1/2 x to the negative 1/2, so 1 over the square root, 1 over 2 square root of c in this case. Now, f of 9 is 3, so this is 9, 3 over 0, 0. And that slope is going to be 1/3. So we know that at some point these two are equal. All right? Which implies that the square root of c equals 3/2, which means that our c value is 9/4. And there is the value of c guaranteed by the mean value theorem. So again, at some point, the instantaneous rate of change, so if I evaluated the slope at 9/4, I would get the same as the average rate of change between those 2 points. Next, if a rock is dropped from a height of 100 feet, its position t seconds after it's dropped until it hits the ground is given by this function. S of t equals -16 t squared plus 100. Determine how long it takes before the rock hits the ground. That's our first step. Well, that would mean we want to find where S of t equals 0, which is -16 t squared plus 100 equals 0. Now, there are two solutions to this. Subtracting 100 divided by 16 and then taking the square root, we get plus or minus 5/2. Now, because we were talking about time, we are only concerned with the positive root there. So it takes 5/2 seconds. So it takes 2.5 seconds in order for us to hit the ground. All right. Well, find the average velocity of the rock when the rock is released and the rock hits the ground. So that would be the slope equal to s of 5/2 minus s of 0 divided by 5/2 minus 0. And that is -40 feet per second. So that is the average rate of change based on our derivative. Oh, nope, not our derivative, just based on our S of t. Now, for the instantaneous rate of change, that we're going to base on that. So we know that there's an S prime of some value c that equals -40 on the interval. And it's going to be in the open interval, -0, well, just 0, to positive 5/2. Somewhere in that interval. Okay, well, the derivative of S of t, it would be our v of t function. That is -32. We'll go ahead and stick a c in there. Equals -40. We want to know where that is true. The average equals the instantaneous rate of change. That would mean that c is equal to 5/4. So at 5/4 seconds, that function, or that rock, is moving at exactly -40 feet per second. Okay. We'll return to proofs for the rest of this. Okay, so go back and check out those other things. Now, a couple of corollaries to the mean value theorem. One is that if a function's differentiable, if its derivative is 0 for all values x in that interval, then the function's constant. Now, that is a very simple proof because we have the mean value theorem. So a corollary means something that immediately follows, something that just is obvious based on some other thing. So it's a corollary to the mean value theorem because the mean value theorem just gives it to us. All right, so if we suppose this function is not constant, but it is differentiable and it's continuous, then there are 2 points, A and B, such that A and B are not the same and the function values are not the same if it's not constant. Well, that would mean we have f of b minus f of a divided by b minus a. And that means that is not 0 because none of those are the same. Or the two function values are not the same and the two x values are not the same, the inputs. So this is not 0. Well, because it's not, or because it's differentiable and it's continuous on this closed interval, then that means there is a point by the mean value theorem and some c. There exists some c value in that interval such that the derivative is equal to that All right. So C exists by the mean value theorem. Okay. Well, that means that there exists a C in that interval, okay, such that f prime of C is not equal to 0. Okay, and that means, or therefore, f of x, or f prime of x, is not equal to 0 for all x in that interval. The derivative can't be 0 then, if that's the case, if we have a point where it's not 0, and that concludes the proof. So if the derivative is 0 of a function, then the function must have been a constant. All right, corollary 2. If f and g are functions that are differentiable in an interval I, and f prime equals g prime for all x in I, then f of x equals g of x plus c for some constant c. Okay, well, let's take the function h of x to be f of x minus g of x. H prime of x then is equal to, based on our derivative rules, f prime of x minus g prime of x. And we are going to say that is equal to 0 because we have this assumption. By that assumption, this must equal 0. F prime of x minus g prime of x. All right. So by our first corollary, by corollary 1, if h prime of x equals 0, then h of x has to equal some constant. Okay. Well, h of x is f of x minus g of x. So that must be some constant, meaning that f of x equals g of x plus c, as we were trying to show. All right, theorem, corollary 3. This is the last one. This is a corollary. However, it's a pretty serious thing to take on. So let f be continuous over the closed interval a to b and differentiable over the open interval a to b. If f prime of x is greater than 0, then f is increasing. We've used this fact previously because it's intuitive. But if the derivative is greater than 0, then this is an increasing function. The slope is greater than 0. If the function's derivative is less than 0, then it's a decreasing function on that interval. I'm going to show one part of this, and then the other one is sort of left to you if you'd like to take it on. It's very similar. So suppose that f is not increasing. So we're saying f prime of x is greater than 0, but f is not increasing. What if that's the case? Then that means there's some points, a and b, such that a is less than b, but the function value of a is greater than the function value at b. All right, well, by the MVT, by the mean value theorem, there is a c, a value c in the interval ab, such that f prime of c is equal to f of b minus f of a divided by b minus a. Now, taking our assumptions here, a being less than b means that b minus a is greater than 0. Okay, b minus a is greater than 0. This assumption here means that f of b minus f of a is less than or equal to 0. Okay, if the numerator here is less than or equal to 0, the denominator is greater than 0, then that means f prime of c is less than or equal to 0. However, we said that f prime of x is greater than 0. Okay? So, however, by assumption, f prime of x is greater than 0 for all x in the interval AB. Therefore, f is an increasing function. Therefore, f is an increasing function because we assumed it wasn't, and we came to the conclusion that that couldn't be the case. So it must be increasing. So part 2 is very similar to this, except you've got actually the only thing that will change is that this this part right here, we would change this to f of a is less than or equal to f of b. So it's probably worth trying if you feel so inclined. All right, that is the end of section 4.4 on the mean value theorem. So remember the hypotheses. Verify those hypotheses are true every time you attempt to use mean value or the Rolle's theorem or these corollaries. That's it.